Have you ever tried to listen to a very quiet whisper in a noisy room? It is incredibly difficult to make out the important information over all the background distractions. Our brains communicate using electrical signals that are thousands to millions of times smaller than the electrical hum from common electronics. Removing equipment noise from neural signals is achieved through a combination of careful hardware design and sophisticated digital signal processing techniques. These methods work to isolate the tiny, biologically relevant electrical activity from the much larger electrical interference generated by recording devices and the environment. The primary reason equipment noise is such a challenge is that neural signals are extremely low in amplitude, typically in the microvolt range, making them highly susceptible to contamination. Sources of this noise include 60 Hz power line interference, which is the electrical hum from alternating current, thermal noise generated by the electronic components within amplifiers, and movement artifacts caused by cables or electrodes. Modern neurophysiology relies on the fundamental principle that neural activity often occupies different frequency bands or exhibits different spatial patterns than these unwanted artifacts. We leverage these differences to separate the signal from the noise. Practically, several key strategies are employed. Analog hardware design focuses on high-input impedance amplifiers with excellent common mode rejection ratios, which means they are very good at ignoring noise that appears equally on multiple inputs, like distant power line hum. For digital processing, techniques such as filtering are used to remove specific frequency bands known to contain noise, like the 60 Hz power line interference and its harmonics. Advanced methods like artifact subtraction use a separate reference channel that captures mostly noise, allowing it to be mathematically removed from the neural recordings. More complex algorithms, such as independent component analysis, can statistically separate different sources of electrical activity within a mixed signal, isolating brain activity from muscle movements or eye blinks. An insider detail to appreciate is the critical role of the common mode rejection ratio, often referred to as CMRR. A high CMRR in an amplifier means it can effectively suppress common noise picked up by all electrodes, significantly cleaning up the signal before it even gets digitized. Another powerful technique is independent component analysis, or ICA, which works without prior knowledge of the noise source by finding statistically independent components, allowing researchers to identify and remove components corresponding to artifacts. Ultimately, the meticulous removal of equipment noise ensures that researchers and clinicians can reliably observe, measure, and interpret the true activity of the brain. This precision is absolutely vital for advancing our understanding of neurological functions and for developing effective brain-computer interfaces that accurately translate thoughts into action.